So let's look at the network design. The network design is another set of problems. Is design problem means you're coming up with something that meet the spec, right? Specifications. So in this case, in the context of network design, we are trying to come up with a circuit that has a network function we want. Right? We first have a network function, and we're trying to come up with a circuit, which is complete kind of the reverse the analysis problem. Analysis problem, you have a circuit, then you're trying to find the network function or the output or the response, right? So this is really a very vast the field with a lot of theorems, stuff like that. So when we are going very tip of this iceberg of we only scratch the surface by using the op-amp. And if you don't use op-amp and realize the transfer function or the network function is much more difficult. And we're going to use the op-amp, especially the inverting op-amp amplifiers and the RC networks. Okay, so we're going to start with the equivalent impedance of the RC network. So we are interested in the faster network. So we're going to look at the parallel R and C. So the impedance for for the capacitance C and the impedance for this C would be 1 over CS, right? So therefore the ZS is for this parallel impedance of the R and the C, that's going to be equal 1 over the admittance 1 over R plus CS, right? Plus C plus CS 1 over CS. So this is the equation. If I divide C on both numerator and denominator, and we'll get 1 over C and divided by 1 over RC plus S, or S plus 1 over RC. So if we have a partial fraction expansion term, then it has the form of K over S minus P, right? So we do the partial fraction expansion, we may end up with something like this. The K is residue. So in this case, if we know this term, we're trying to decide the R and the C value, and we can see that K is going to be equal 1 over C, right? And negative P is going to be equal 1 over RC. So if we write this equation here, so that's going to be equal C is equal 1 over K, right? So the C value should be easy to determine. That's just 1 over the residue, and the R is going to be equal 1 over C divided by negative P, or the negative 1 over C times 1 over P, right? So 1 over C, that's a K, so that's equal negative K over P. Or you can think of this more conveniently, that's equal K over negative P. And so this value of the capacitance and resistance, and will give you this term. So let's see if we have a general term. So if we have the ZS in a more general term, that's maybe equal to K0 over S plus K1 over S minus P1 plus K2 over S minus P2 and plus Kn over S minus Pn and plus a constant term. And in this case, this constant term K sub infinity, because this, we call this as has a pole at infinity. And in this case, we have this is going to be the resistance, and this is going to be pure the capacitance. So we can get the values as 1 over K for capacitance, and this one this one will be the parallel R and C, so that it has a value 1 over K1, and the resistance is going to be negative K1 over P1. So this is the general form, and this resistance will realize this partial fraction expansion terms, and this is called commonly known as a Foster network. Okay, and Professor Foster made a lot of contribution in the circuits. He did a lot of work in 1930s, and he just passed away in 1998. Right? He was 102 years old. So let's look at a couple of examples and see if we can get something working. Okay. So let's see the first example here. We are trying to design a circuit to realize this transfer function using the resistors and capacitors and op-amps. So remember the op-amps, if we have a negative sign, so we have the op-amps, we have what we call the inverting op-amps, so that have Z1, so this is the inverting terminal, the non-inverting terminal, they connected to the reference node, and let's call this, so here, let's see, this is the V1, and this is VO, this is V2, and this is Z2S and Z1S. And the inverting amplifier has the voltage transfer function of V2 over V1 is equal negative Z2 over Z1. Right? So the goal here is we're trying to put this transfer function as the ratio of two impedances, and then we can realize that impedance by the resistors and capacitors. Okay, so in this case, let's first do something. We can't really do. Let's see. Can I take this as the resistance, as the impedance Z2, and this as Z1? In that case, you can't really realize S by using the capacitance, right? So you have to use the inductance. So what do we do is we first divide this S by divided the numerator and denominator by S. So in this case, multiply 1 over S and multiply 1 over S. And what we get here is 500 on the numerator. On the denominator here, we have 1 plus 1,000 over S. So in this case, we want so now possibly we can see if we choose Z2S equal 500 and Z1 is equal 1 plus 1,000 over S. This could be a resistance, this 1 ohm resistance, and so in this case, what the capacitance for this term? The capacitance C is going to be equal 1 over K. That's equal 1 millifarad. 1 over 1,000. So that's 1 millifarad. This doesn't meet the requirement. We want to use smaller capacitance, right? So in that case, we need to have a K is equal 10 meg, which is 10 to the power 7th. So we need to multiply. What I do is I multiply TV, that's equal negative 500 divided by 1 plus 1,000 over S. I multiply that by 10 to the power 4th. I multiply both sides by 10 to the power 4th. So in this case, I will have the 5 times 10 to the power 6, right? So in this case, divided by negative here, divided by 10 to the power 4th plus 10 to the power 7th over s. Now I can let z2 is equal 5 times 10 to the power 6, and z1 s is equal 10 to the power 4th plus 10 to the power 7th over s. So z1 is going to be series resistance and the capacitance in connection, and z2 is just a resistance. So if I draw the circuit, and this realized circuit would be something like this. So this resistor is a 5 mega ohm. Did I make any mistake? So that's the 5 mega ohm, and the input side that I have the capacitance 0.1 microfarad, and the resistance is just a 10k. Right. So here this will have the V1 and this is V2. And sometimes we just label V2 as node voltage. And so this is the realized circuit. So this is simple example shows how we come up with the so-called the network design. Let's look at another example and see if we can figure this out. So in this case, I have the I have a transfer function slightly different. I still have a negative sign here, and in this case I will divide s. So I will divide s on the numerator for the numerator and denominator. So in that case I got 1 over s times 1 over s. And in this case, I would like to take the 1 over s combined with the first term. We'll see a moment y. So 1 times 1 plus 1000 over s, and s plus 100, right? So in this case, what I'm having here, I would recognize this one as z1, and this one as z2, and this one as z1. So in this case, I'm having negative z1, z2s over z1s equal to 1000 over s plus 100, and 1 plus 1000 over s. So this Z2 gonna be a parallel connection of R and C, right? So in this case, if we do the Z2 is equal to 1000 over S plus 1000 and S plus 100. So in this case, the C gonna be equal 1 over K. Again here, that's 1 millifarad. That doesn't meet the requirement. We want to use only very small capacitors. So we need to do something. We need to scale things up, right? So what we do is we multiply this by 10 to the power 4th. We multiply by 10 to the power 4th. So in this case, I got a 10 to the power 7th over S plus 100. Now I have 10 to the power 4th plus 10 to the power 7th over S. And now the Z1 is, so this Z2 doesn't work. And I would like to have Z2 is equal to 10 to the power 7th, S plus 100. So in this case, let's call C2. C2 is going to be equal to 1 over 10 to the power 7th, which is 0.1 microfarad. And R2 is just equal K over negative P, which is 10 to the power 7th. Negative P is 100. And therefore, this is 10 to the power 5th. Right? So that's 100 kilo ohms. And for Z1, that's equal to 10 to the power 4th plus 10 to the power 7th over s. So the C1 is going to be 1.1 microfarad as well. And R1 is going to be equal to 10 to the power 4th, which is 10 kilo ohms. So now I can have a circuit that should work to give us this transfer function, the inverting amplifier, and I have the series connection, the resistance and the capacitance 0.1 microfarad, and I have a resistance of 10K. So this is the input voltage V1S, and I have the parallel connection of the resistance that looks like an inductance. So the resistance and the capacitance. So this is V2 here. So that's for, and this resistance is going to be 100K and the capacitance 0.1. And sometimes you can't really realize this with one op amp. You may need multiple op amps. You may need to break this the transfer function as the product of the ratio of the impedances. In that case, we call them multiple stages, and the more complicated problems out there, many. Okay, so here we only introduce this at on the very surface level. Okay, so hopefully you can, if you're interested in there's more systematic approaches of how to realize this. The work mostly was developed in 1930s to 50s, and recently there's a few newer publications in 2000. After 2017, there was some more recent work, but most work developed in the around the Second World War that time. Okay, so that's about it for this lecture, and no matter what you do, keep going, never stop, right? So I'm gonna see you next time.